Welcome. In this video, we are building something powerful, an AI agent that can think, make decisions, and correct its own mistakes. If you have used LangChain before, you know chains are great for linear workflows. But real agents need more. They need to look at a question, decide which tool to use, check if the answer is good enough, and retry if it is not. That is what LangGraph does. It turns your linear chains into a flowchart with branches, decisions, and loops. By the end of this explanation, you will be able to build a complete agent that routes questions to different tools and checks its own work. Let us get started. Let me show you the fundamental difference. A chain is like an assembly line. Data comes in, goes through step 1, step 2, step 3, and comes out the other end. Always the same path, always the same steps. Great for simple tasks like answering a question or translating text. But an agent is like a flowchart. It needs to think about the question first. Is this about a dam? Use the dam tool. Is this about rainfall? Use the rainfall tool. After getting an answer, it checks if is this answer good enough? If not, go back and try again. That is branches and loops. A chain cannot do that. A chain only goes forward. LangGraph gives us graphs, nodes that do work, connected by edges that can branch and loop. Let me show you the three building blocks. Every LangGraph agent is built from exactly three things. First, state. Think of it as the agent's shared notepad. It is a Python dictionary that flows through the entire graph. Every node can read from it and write to it. It holds the user's question, conversation history, tool results, and the final answer. Second, nodes. These are the workers, plain Python functions. One node might classify the question, another fetches data from a database, another generates the final answer. Each node takes the state, does its work, and returns updates. Third, edges. These are the roads connecting nodes. Fixed edges always go from A to B. Conditional edges use a decision function to choose. Do I go to B or C? This is what gives agents their power to make runtime decisions. The analogy is simple. State is the notepad everyone shares. Nodes are workers sitting at different desks. Edges are the hallways connecting them. Some hallway fork based on what is written on the notepad. Let me show you the code for each. Here is the state definition. We create a class called agentState that inherits from type dict. It has four fields. Messages stores conversation history. Current underscores query holds the user's question. Tool underscore output stores results from whatever tool runs. And final underscore answer is what we return to the user. Now, look at the highlighted line. Messages uses this special annotated syntax, that is annotated square bracket list comma operator dot add square bracket. This is crucial to understand. Normally, when a node returns a dictionary with key output messages, code pointing to a list with one new message, Python would replace the entire messages list. You would lose every previous message. With operator.add, returning that same dictionary appends the new message instead. The old ones stay. The new one gets added at the end. This is how conversation history builds up automatically as the agent moves from node to node. Get this wrong and your agent has amnesia. It forgets what happened 2 steps ago. Get it right and every node can see the full conversation history. Here is what a node function looks like. This is a router node. Its job is to classify whether the user is asking about dams or rainfall. Every node follows the same pattern. Step 1. Read from state. Here we read state square bracket quote current underscore query quote square bracket to get the user's question. Step 2. Do work. We build a prompt and call the LLM to classify the question. That is llm.invoke open parenthesis square bracket human message open parenthesis content equals prompt close parenthesis square bracket close parenthesis. Return a dictionary with only the keys. That is step 3. Return a dictionary with only the keys you want to update. We add a new message to the messages list and store the classification in tool underscore output so the next node can use it. Notice, we do not return all the state keys, just the ones we changed. LangGraph merges our updates with the existing state automatically. And remember, because messages uses operator.add, our new AI message gets appended to the existing list. The agent remembers everything. This pattern is universal. Every node you will ever write follows this exact structure. Read state, do work, return updates. Building a graph is always the same 4 steps. Let me walk through each one. Step 1. Create the graph with state graph, open parenthesis, agent state, close parenthesis. This tells LangGraph what data the agent works with. Step 2. Register your nodes with add underscore node. First argument is a string name. This is how edges will reference it. Second argument is the actual Python function. Step 3. Set the entry point. Which node runs first? Every graph needs exactly one entry point. In our case, the router always runs first to classify the question. That is graph.set underscore entry underscore point open parenthesis quote router quote close parenthesis. Step 4. Compile. This converts your graph definition into a runnable agent. After this, you can call agent.invoke open close parenthesis just like you called chain.invoke in LangChain. But wait, we added nodes but we did not connect them yet. How does the router know whether to go to dam underscore tool or rainfall underscore tool? This is where edges come in, and specifically conditional edges. That is the next slide. This is where LangGraph becomes truly powerful. Conditional edges. Look at the diagram. The router sits at the top. When it finishes, it does not always go to the same place. It checks what it classified and routes accordingly. Dam questions go left to dam underscore tool. Rainfall questions go right to rainfall underscore tool. The root underscore query function makes this decision. It looks at state square bracket quote tool underscore output quote square bracket, which is where the router stores its classification, and returns a string. That string maps to the next node name. Then we call graph dot underscore conditional underscore edges with 3 arguments. First, the source node, which is quote router quote. Second, the decision function, which is root underscore query. And the third, a mapping dictionary that converts return values to node names. So, quote dam underscore tool quote maps to dam underscore tool and quote rainfall underscore tool quote maps to underscore rainfall underscore tool. This is the heart of what makes an agent an agent. It does not follow a fixed script. It reads the situation, what did the router classify this as, and picks its own path at runtime. This is the most powerful pattern, the self-correcting retry loop. Look at the flow. 3 nodes. Fetch underscore data gets the raw data. Generate underscore answer creates a response. And quality underscore check evaluates it. Here is the magic. If the answer is not good enough, quality underscore check sends it back to generate underscore answer for another try. The should underscore retry function is the decision maker. It reads state square bracket quote quality underscore score quote square bracket. If it equals quote retry quote and state square bracket quote attempt underscore count quote square bracket is less than 3, it returns quote retry quote that makes back that, that maps back to generate underscore answer. The agent loops back with a stricter prompt that says you must include specific numbers. If the quality is good or we have hit max retries, it returns quote done quote that maps to end. The agent exits. The attempt underscore count less than 3 check is critical. Without it, a persistently bad answer would loop forever. Always cap your retries. This is what separates a toy demo from a production agent. In the real world, LLMs sometimes give vague or incomplete answers. The retry loop catches that and forces the agent to try harder. The pattern is also the foundation for text to SQL agents. When the generated SQL query fails, the agent loops back, reads the error, and fixes the query automatically. Let us run the agent and watch it think. On the left, we use agent.stream instead of invoke. Stream shows each node executing step by step. It is like watching the agent's brain in real time. On the right, the trace. First, the router runs. It classifies the question as quote, damn, quote. Then, damn underscore tool runs. It extracts quote, Srisalam quote, and fetches storage data. Finally, the answer node generates a response using that data. The comparison table at the bottom shows how this maps to the old way of building agents. Instead of while true loop, you have graph edges. Instead of if-else blocks, you have conditional edges. Instead of manually passing state between functions, agent state handles it automatically. And instead of print open close parentheses statements everywhere, agent.stream gives you structured traces. The concepts are identical. The implementation is a bit simpler. Now, let us recap LangGraph. 6 concepts. State is the shared dictionary that flows through the graph with auto-appending messages list. Nodes are Python functions that do the work. Edges are connections between nodes, either fixed or conditional. Routing means decision functions that inspect state and pick the next node. Compile converts the graph into a runnable agent using graph.compile open close parentheses, and the retry loop lets the agent check its own work and try harder if needed. The formula is simple: state plus nodes plus edges, compile, run. This graph structure is the skeleton for any AI agent you will ever build. Want to add a new tool? Add a node and edge. Want the agent to search the web? Another node. Want it query a database? Another node. The graph grows, but the pattern stays the same. This is what I wanted to talk about in this video. Thank you.